Buenas tardes. Let's see who's here. I think I'm the only one in right now. Should I start? Is the question. So if I do get started without anybody in the space, it just means that you can watch it on your own time. The last 2 weeks, I asked all of you to review statistics, and I gave you a number of resources. I gave you lecture notes, and I gave you videos. I also gave you problems to solve, and it was all video recorded. I wanted to add on one more piece, but I'll wait until I arrive at that point in the notes to demonstrate how it is that you can enter ex-ante data into the TIBA2+ to compute a variety of statistics. So let's wait for that. Maybe 1 more minute. Oh, looks like people are unaware that I'm here. But I'm going to continue with the lecture. Okay. So what I had you do was review statistics, and then I ended up introducing financial data and financial statistics, which are equivalent, but just with different, more specific data. In particular, returns data. So what I want to spend some time doing is discussing where the returns data comes from. Oh, did I lose? You lose the image? Hold on. You lost the image. Why is that happening? Okay, well, the image shows in my feed, but it doesn't seem to appear for whatever reason here. Oh, I know why. Okay, now it works. Okay, so where do returns come from, or how are they computed? Let's consider the very basic case, okay, of stock that pays a dividend, all right? And what would be the return on that asset? So over a set period of time, you could be looking at returns over a year. You could be looking at returns over a quarter or a month or a day or instantaneously. Okay, so I'm going to just refer to the distance or the duration of the period over which you are considering calculating the return as T to T. I'll say, let me do it like this. So we're going to go up to T from T minus 1. Now I could do it different ways. I could do T to T plus 1, but I'm going to do it this way, right? And so this would be now, and this would be next period. It's a little bit different when I was using T and T plus 1 or T and t+1, that's mostly what you saw before, but now I'm going to do it like this, particularly because I want to talk about a reference point and in relation to the period I'm interested in, which is next period. Okay, so to calculate the return in dollar terms for stock or any asset, you consider if there's a dollar return. So for stock particularly, we call it a dividend. And then a change in market value. So if the sale price of stock increases as a result of recent information, then that should be also included in the return, because a person holding that stock has realized if they were holding it from now to next period, or I could also talk about this. Hopefully this doesn't, this is probably the better way. You could say this T is now, and T-1 is last period. Okay, the point is that there's a distance of one period, whatever that is. As I mentioned, it could be a year, it could be a day, and it could be instantaneous. So just as some examples. So what does that look in terms of, how do we look at that in terms of a percentage return? That's how the data was presented to you, as a percentage return. Well, we should take the dollar return, which is all of this, and divide it by the beginning market value to figure out the percentage return. So if we use the symbols, dollar dividend being DT, D for dividend, and T for time T. And the change in market value we mark as the change from last period to now, or now to next period. Then what we need to do is divide these to see the change by the initial price. So that's what we're going to do. So the beginning, we divide that by the beginning market value. So we take right? So we put everything in reference to what it was originally to see a change. All right, so then this is the percentage return, these two parts. The first part we'll call the dividend yield as a percentage, and the last part as capital gains yield. All right, so everything relative to the original price, or the price last period. So I feel like we're going to most likely talk about it in this terms, right? So I'm going to use T-1 for last period and T for now. The point is that they're one period apart. Okay, so let's look at that. Let's give that a name. So I'm going to call that RT, R sub T for returns, time T. And although I've talked about it as last period and now, or now and next period, the point is that I could do this at any point in time T. Okay, I could calculate this at any point in time T, looking back to the previous period's price to compute the percentage return. So you need information on the dividend received and prices to calculate this. So we can write this percentage return this way. We could also write the percentage return rearranging in this way, where we take the dollar return plus the price today and divide by the previous price and then subtract 1 to get a, so basically that, like, what's the percentage, right? We're taking off the principal for every dollar invested. In other words, this is just the percentage that results in return. Right, so this is per dollar invested. I could also write it like this, as I discussed, dividend yield plus capital gains yield. Since there's nobody there making calculations, I'll just ask you throughout the video to pause the video and try and make the calculations yourself to ensure you can make them. All right, so let's look at this a little bit more. I'm referring to these returns, historic returns, as ex post. Okay, ex post is literally after the fact. Okay, after the fact. So this is data that was collected. We're at some future point relative to this data. And so we're looking at a list of returns. So for instance, just like I provided you with a list of returns for the stock and what I call the market index, you were able to compute statistics of those returns, okay? Now, the particular thing about these returns is no pair of returns or no set of data each year is more important than any other. Okay, they have equal significance, and the statistics are computed with that in mind. I want to make the point now, like in economics, you probably learned about the measure of a percentage change. And when we calculate a percentage change, we do so by taking, I'll write it this way, a new value minus, so whatever variable you're interested in, let's say it's returns, or let's say price, okay? So if I'm interested in price and looking at the percentage change in price, so the percentage change in price of stock, then I take the new price minus the old price divided by the old price. So that looks familiar. So now I'm referring to T and T minus 1 as new and old. And that gives me the percentage change in price. All right, so that's something you should have seen in your studies before. So I'm using that idea over here. So now we have a new way of talking about these. I could call this one old and this one new. Okay, so I'm just looking at different ways to think about T minus 1 and T. So you can think of it as old and new, last period and now, or now and next period, or just t minus 1 and t. Okay, another point. Now looking here, this is the formula I gave you. At any point in time t, we could calculate, given we have the variables or the values of these variables, price and dividend, we could calculate the return at time t this way, and I explained why. We could also rearrange these values, or these variables, this way. And how can I do that? Let's see. I can first of all call this, referring to the percentage change, as the growth rate over that period. So that's something, so that's a revelation, right? Something that I've talked about before, but not exactly or precisely like this. So I'm going to rename that G. Now, in doing that, what I'm going to say is, let's say, kind of making an assumption here. So if I assume that the relationship between price and dividends over time is consistently like this, I'm going to call dividends, oh, I lost power. Dear, hold on. Buenas tardes, Ricardo. I'm having a little difficulty with my iPad right now. I'll be right there. All right, so you can see my iPad. Just a moment. So you don't see that, do you? Okay, wait, I have to do something to make you see that. Oh. Screen. Okay, you see that. If I do this, you can see. Okay, so you should be able to see that. Oh, you can't see it all. Oh my goodness. Okay, so I need to set all this up. Oh, it's not going to work. Oh, forget that idea. Oh, maybe. I'm having a heck of a time because I can't seem to charge my iPad and use it at the same time. I have it plugged in here. I don't know why it's not charging. Usually it charges. I'm in trouble here. Oh, okay, I see what I can do. Make it smaller. I have a lot of work to do. This is not gonna, it's not gonna be easy enough. Okay, okay. Okay, maybe this will work. One more time. Okay, give me a few minutes, or half a minute. I'm gonna have to totally edit this video, so you're gonna lose the chat. All right, so here it goes. I'm just looking at it, whether you can see it. All right, so you can see my iPad now. All right, so what we're doing here is computing returns data. And to do this, I explain you need data on prices. And in particular, we're going to focus on returns data for stock. So we're going to need data on dividends. And I explain that the dollar return is where we begin. Now, a dollar return over a period of time, which we will use t-1 to t to mark the intervals of time at any point in time. But the difference is that t-1 will be considered as, well, I'm pretty much going to call it last period, where t is now or today. Okay. I may also refer to t-1 as now and then t as next period. Depends on what I'm focusing on and the data, the way it's presented. I can also refer to old and new, t-1 and t. The point being that it can be at any point in time and it's a difference of one period. So I can calculate the dollar return on the asset and then the percentage return on the asset by taking the dollar return and dividing by the previous price. So there's a reference point. And what I get is what I call the first piece being the the dividend yield. And we call the second piece capital gains yield. I can write it all as one quotient, I can also write it this way where it's like for every dollar invested, I'm realizing a percentage return. So this is showing if you algebraically separate these two terms from this one, this becomes a 1. So in other words, subtracting off the principal, right, of the investment, then what it's left in terms of percentage return. And I can also write it like this, which was the first way that I presented things. Then I remind you that you've seen this sort of calculation before, the PT minus PT minus 1 divided by PT minus 1, or the new price minus the old price divided by the old price is just a percentage change in price. So another way to look at this is a growth rate in price. Now, presuming this relationship holds throughout time, I can make it a constant G. So assuming, I thought I already wrote this, but it seems to have disappeared. Assuming the relationship between prices and the dividend do not change over time, then I can say that this is going to be the constant growth rate. If the first dividend is the constant dividend, then I can just call this dividend C1. And then the original price I would call PV0, where the return represents the rate of return, or I in the symbols that I've used before. So what I'm doing here is making this assumption that the relationship is constant, rewriting this like this, and notice that you've seen this before. This is just where, this is what we use to calculate the price of a stock. So it feels like I've come full circle. The difference between what I've explained today here and what we did before here is that we assumed the relationship between prices and dividend was constant. So it's a constant dividend, and the change in prices remains constant with a G growth rate. Okay? So in other words, this is a more general formula of what we had before, or more general formula of what we've been using so far. Let me just write that. So this is a general case, where this is more specific. Okay, with that in mind, let's look at computing, given this information, the total percentage return, and then partitioning it into the dividend yield and the capital gains yield. So why don't you try that? So working through this, suppose a stock had an initial price, so this is the initial price. This is PT minus 1 per share, paid a dividend of, okay, so that was just during the year, so we'll call that DT, and had an ending price of 46.2. So putting that together, and I'm just going to use T because I don't know when it was. Or I guess you could use R1 and 0. So let's do that. Let's do that. So like R1 is equal to D1 over P0 plus P1 minus P0 over P0. You can write it like that, or you can just use the T's. I'm fine about it. As long as you understand and you're clear and consistent, it should be fine. So I'm going to use the T's because I use T's up here to avoid confusing you. So let's do that. So RT is equal to DT of 84 cents divided by last year's price, which is $42 minus 46.2 minus $42 divided by $42. So 84 cents divided by 42 gives 2%. And then 46.2 divided by 42 divided by 42. Did I say? I said 46.2 minus 42 divided by 42. Is 10%. And it's an add. I don't know why I put minus. It's an add. So this is 12% total. So the dividend yield is 2% and the capital gains yield is 10%. Okay. Oh, it looks like I don't have a good version of this document. So what you should be looking at now, these are the lecture notes. I'm going to double check that they are visible for you on the platform. So those are like multiplication products terms. I'm going to check in the platform. 1 minute. I'm just checking that I've opened this document for you to see. In Unit 5, no, I have to open it. Okay. Okay, you should be able to see it now. Yeah. Okay. All right, so what does this say? This page is all about different statistics. You might be interested in looking at the returns. So you'll have, as a result of making the returns calculation, you'll have something like so that's what you're going to get, right? So in each year, you're going to be able to calculate these returns based on dividends and prices. And this is the ex post data I talked about, where each observation is just as important as the other. Now, what if I want to know from year 1 to year 4, what's the return overall? So that would be compounding 10%, 15%, 6%, and 8%. Well, that's what this does. This gives you a holding period return for each dollar invested minus 1. Right? So return for each dollar, compounded return for each dollar invested minus the principal 1 for each dollar. And that's useful if you want to talk about how much you made over 4 years or a period of time for every dollar invested. What if you want to be able to compare different assets that you invested in, but on an average basis? Like you want to look per year, what was the return? So to do that, we can get an average. This is the traditional average, right? Or the arithmetic average, where you add all the returns and divide by how many there were. This is just an arithmetic average. That's different than looking at the return as the holding period return and partitioning equally by using the exponent. Okay, so this should feel like more like when we did interest rate conversions, right? Now, this method is better when the data are skewed. Okay, so this method, geometric average return, is a better measure in general than just doing the arithmetic average, because the arithmetic average is prone to extreme values. So if you have a few high returns, it will make the overall average a little bit higher than really is the case on average or across those periods. It gets distorted, in other words, okay, about those very high values. And similarly, for those very low values, it gets distorted to make it look like the average return is actually smaller than we'd like to say, kind of neglecting the relatively higher values. So we prefer the geometric average return when there's a difference between the average and the median return. I'll say when there are skewed returns data, use GAR. Okay, GAR is not sensitive to outliers. Again, you should, if you don't know what an outlier is and you didn't take time to do the statistics review over the last 2 weeks, go back and do that review. I'm going to assume you've done it. All right, so with that in mind, let me give you some data. So this is not good. So this is because I've opened the file that's a doc file. I'm gonna have to go get the other one. Okay, so this is in the lecture notes on page 5. So let me stop this for a moment and get the other file for you. Okay. Okay, so here are, I'm gonna open this for you. Okay, you should be able to see this. All right, so these data are returns data from 2007 to 2010, which you recognize are the years of the global financial market crisis. And I've taken these actually from this website here that stores return data. This actually is from the S&P 500 index. So this is a measure of market performance, a market portfolio performance. So it looks like how the markets did. Okay, so if you invest in a diversified portfolio of stock, risky assets, then this would be your approximate average return in 2007. This would be the return in 2008, 2009, 2010. And looking at this data, there was a very large historic drop in 2008. This is a huge loss for investors for dollar invested. But did they recover? That's kind of the question we want to look at here. So let's calculate each of these. We're going to calculate the holding period return, geometric average return, and the arithmetic average return. Can you guys do that? Give you a moment to do that. So what you get are these calculations. You find a holding period return that's actually negative. It's a slight negative, but essentially you lost money over those 4 years if you invested in the stock market. What was your return on average? Well, this shows, this geometric average return calculation shows that your average return was like a negative 1%. In particular, it was, to be specific, it was negative 0.84%. So almost negative 1%, which is in keeping with what you see here, 3.3%, and negative 3.3% overall the 4 years. Now, this is really important, okay, what I'm going to show you next. If we just calculated the average return, those high returns of 26% and 15% relative to the other low returns and the extremely low 37 negative percent in this 2008, when you put those together as an arithmetic average, it looks like there was an average of 2.5% every year. That's very misleading, you see, because overall there was a negative return, and each year there was a negative return to make that overall negative 3.3%. But that is not what the arithmetic average shows you, all right? So we prefer, when these differ, go with the GAR. And you'll see that this is relatively skewed data. So typically when GAR and R differ, use GAR. As the average return. So you're going to use, this is your overall 4-year period return, and this is your average return. Questions? So you should practice calculating those. Make sure you can get the numbers I get. And you got to be careful with these negatives. Well, this negative. Okay, so let's look at this is a set of data that I took from this website that I've indicated here. What you see are the returns for different asset classes. We begin with the S&P 500 as a measure of the returns on a well-diversified portfolio of risky assets, in other words, stocks. Okay, and these are the top performing stocks. So these are the best performing companies' stocks. Or stock. And so if you take the bold line, you see it's the most wild of the trends that I'm demonstrating between 1928 and 2016. I have not updated this with the most recent data over the pandemic, and that was kind of that was a period, again, with particular circumstances, but over the long haul, over this 80-year period, I don't suspect it will have that much of an impact on the overall statistics, but I guess I should include it to check. At this point, this is enough to show what I want to show you is that the most volatile of all the trend lines are the stock return data. Much more wild Then 3-month T-bills. So these are treasury bills. These are bonds sold by the government to borrow money from the public with a guaranteed return after 3 months, the face value of the bond. Okay. And in there is implicit a yield to maturity, a yield that is going to be like a return that is lower than the return on stock, because that's a trade-off of the guarantee. So you're guaranteed to get that return. And usually the return on 3-month T-bills is higher than inflation, right? So people are attracted to the T-bill to loan money to the government in return for keeping up with inflation as a result of their investment. So that is going to be the thinner line. You'll see that a thinner dashed line is actually the least volatile, right? It's very steady in between those other two, being the S&P 500 and the 10-year bond. So the 10-year bond has more risk. It has to have a higher return because it needs to incentivize people to lock in that rate for a long period of time. But still, having said that, it's still not as volatile a return as stock because there is a guarantee. The risk, though, is that is a long period of waiting that leads to uncertainty and requires a higher rate of return when compared to the 3-month T-bill. Okay, and that is the dashed line that's in between in terms of volatility. Okay, so how do we measure volatility? While the return measures reward, we need some measure of uncertainty or variability associated with that return, and that's what we use the statistic known as the standard deviation to compute. So here are so this should be a review again. Well, this is applied statistics, right? So you learn statistics. I introduced you to the variables for finance, and now we're applying what we learned. So here are the statistics I taught you, the variance and the standard deviation. The variance I write as variance of the returns, or S for ex post data, so historical data. I also can use this symbol sigma with a hat on it, and it has a hat on it because this data is not, the statistic is an estimate, right? It's an estimate. So that is noted by the hat on top. It estimates the parameter sigma. Okay, again, if you don't recognize any of these symbols, you need to go back and watch the videos on the statistics review. All right, so this is how we calculate the standard deviation of ex post data. We take the variance and we take the square root. So with that in mind, let's do that. So we calculate, you can do it manually or you can just use your calculator to get the mean and standard deviation. So let's do that together. The standard deviation is very high. It's 27.69. Whereas the mean was, we're going to use Well, we like to use the 0.84% negative as our geometric average return. But we are going to use, when we use the standard deviation, the way I taught you, we use it together with the arithmetic average return, all right, to make our point. But as a single measure, we should refer to the GAR. That's what I've said here. So let me show you how to put this in your calculators. You should know how, but I've done it 2 different ways with the tables. You can do this in Excel. But let me show you the easiest way on your calculators. So I want to go into stat mode of the calculator. And it says LIN, L-I-N. L-I-N stands for linear. It's set up to make a linear, the calculator can take 2 variables at a time. And as a result, it can compute the relationship between 2 variables at a time, known as the correlation coefficient. And it can estimate the linear trend as the least squares regression line. Okay, so that's what the LIN stands for. So again, if you don't know what I'm talking about, go back and see those videos. All right, so what I want to do is first enter the data. So I hit second data and I make sure there's nothing there. So there's nothing there, it's clear. If it's not clear, I have to hit second clear work. It's a worksheet to clear. So second data, and I enter the values as decimals, 0.0549. Enter, and there's only one of them, so continue. 0.37 negative, enter, it's only one of those, and then 0.2646, enter, and there's only one of those, and 0.1506, enter. Okay, so I have all the data, the first one, the second one, the third one, and the fourth one. And now I ask for the statistics, I get the LIN, and I use the arrow to scroll down. There are 4 observations. The mean is 2.5. We know that was calculated. The standard deviation is 0.2769 or 26.69%. And this is the variance as though we have all the data. If we had all the data, we would use this number instead. But because we only have a sample, we use the sample standard deviation instead. Right? So that's how I get those results. Now the other information that data gives me, or sorry, stat gives me, are related to the relationship, but I only entered 1 variable. I didn't enter 2, so it's rather meaningless. Okay, so what I'm going to do next is take that information and put it into a bell curve, right? So what am I doing when I do that? What I'm doing is I'm assuming that the shape, well, I actually have all the data, so I could actually make a histogram. And you will find that the histogram will be relatively symmetric. In fact, I have below here you have the histogram for data over the period 1926 to 2008, and I actually have another one here. This is for the data that I gave, that I put into the chart that we discussed, the 3 asset classes. So here are the data from that chart over here. Where's the chart? Here. So that's the data 28 to like 1928 to 2016. And here is what it looks like if you make a histogram. So it's not perfectly symmetric, but it's relatively symmetric, okay? I know when you get more comfortable with statistics, you'll be more comfortable making statements like I'm making, that this is relatively symmetric. And we're going to talk about this page in a moment. Just to show you, though, what we're going to then do is assume it's symmetric. And we're going to make the density curve and interpret it. I have trouble making this. Okay, that's the best I can do right now. And then, all right, and we're going to put in the middle will be the mean. So assuming symmetry. Notice that I mentioned I'm only using those 4 years of data. 4 years I used. But I'm going to assume this shape, okay? So how can I do this? Why can I do this? If I had more data, the idea is if I had more data, more detailed data like daily returns or monthly returns or quarterly returns, I believe I could get this shape. And the mean will be 2.5%. And the standard deviation will be that 26 or 27%. So what I'm going to do is divide this up. So now that I've drawn this, and I'm saying this is representative, we're taking our sample and making it representative of the whole population. Let me remind myself of 27.7%. So let's just say 28%. Or no, let's use one decimal place. So we're going to say the mean is at 2.5%. And I'm going to spread out the data like this. What am I doing? There. Okay, so I want you to replace those with numbers and then answer these questions. What is the chance of positive returns approximately? What is the chance that returns will be less than negative 30%? That's what I want you to do. What do you get? So using 26.7%, so mu is equal to 2.5 and sigma is 27.7. Imagining that that represents all the data over that period. I'm going to replace all these numbers. So this one would be 30.2%. This one would be 57.9%. And this would be 85.6%. Very high. So it looks really great. Oh, wow, it can get 30% within one standard deviation. Wow, that's amazing. But what about the downside? Within one standard deviation, you can have a negative return of 25.2%. And at 3 standard deviations, 80.6% negative. So this is quite wild and volatile, very high standard deviation. Oh, yeah, that was a standard deviation. I'm just checking to make sure. Okay, yeah, that's a standard deviation. So what is the chance of positive returns approximately? Okay, well, this is not exactly 0 for a positive, but I can approximate and think about, well, approximately 50% of the observations are greater than 2.5%. Well, 50% are greater than 2.5%. So approximately 50% chance that they're greater than 0. What is the chance that returns will be less than negative 30? I'll use this one here to estimate that. And we know at 1 standard deviation, or between 1 standard deviation are 68% of the observations, right? So then that means on just one side, it's 68 divided by 2, or 34%. So don't get confused that our variables in percentages, but then we're talking about likelihood. Try and keep that clear in your head. So just remember, this is the variable. What's the chance of being lower than 25.2? You can leave the percentage out if that confuses you, and just remember those are returns in percentages. And then refer to less than 30%, approximately 34% chance. Something like that, because you could also say it's smaller than 34%, because up to here is 34, but negative 30 would be here somewhere. So anyway, but those are the numbers I know for sure at the large tick marks. All right, so let's see. Sorry, let's see. What I mentioned to you. the data gets all the notation gets unglued. Okay, there we go. All right, so what we have here are the data over this period, 1926 to 2008, for risky assets or large company stocks. This is a histogram that you would get with the data, and I got this from this source. What I want to show you is that whether you go up to 2008 or you go even further and update it, and if I was to even update it more, so if I go to 2016, you're going to get practically the same results. And even if I add 2022, it's going to be very similar. So what am I looking for? I'm going to look at, this is the arithmetic mean, which, remember, we use it to make the histogram for relatively symmetric data. And we use it together with the standard deviation to do that, to create that density curve and interpret or make predictions about what to expect. Now, I realize I contradict myself because initially I said that the GAR and the arithmetic average will be different when the data are skewed, and that in that case we should use the GAR, and then I proceed to make this density curve as though it's symmetric. So just bear with me because I didn't want to create a new data set. I use the same data set, but that's what you're doing. Once you make a histogram, a density curve with the histogram believed to be underneath. When you do that, you're just assuming symmetry, which I just showed you that it's probably not symmetric, but just go with it, okay? Because I wanted to practice interpreting the density curve, because in general, over time, whenever you take a large period of time, this is only 4 years of data, but if you take a lot of data, a lot of years, you're going to see it's pretty stable. And so let me show you that now before we go. So here you have this data is used to calculate the mean and the standard deviation for large company stock, smaller company stock. These are even more risky, right? So these are smaller company, more risky. I know it's more risky because of the standard deviation and also because the accompanying average return. Much more volatile. Look how much more spread out these data are. Noting the greater volatility of the data. And then we turn to bonds, and corporate bonds are a distant third in terms of asset classes and returns. And it's accompanied by a lower standard deviation. Long-term government bonds, more secure, less risk, so that's a lower return. And notice there's some inconsistency here, right? Usually we see a higher return is accompanied by higher risk, but not in this case. This is more volatile in terms of prices or returns calculated from prices. This is the T-bill. So this we see as the as higher than inflation, like I promised you, on average over this period, right? T-bills beat inflation with the lowest standard deviation of all asset classes. And you'll see that we will proceed with referring other assets to the T-bills. We're going to refer to T-bills as the risk-free asset. Even though there's volatility, relatively speaking, it's risk-free. All right, and we've calculated here inflation and the standard deviation of inflation as well over this time period. So if I take, let's take these, well, let's remember this number, 11.7% for large company stock and the T-bill 3.8. And if I go over a larger period, you'll see it's very similar, 11.4% using the S&P 500. And the T-bill on average is 3.5% versus 3.8. So very similar results. And what do I do with this information? Oh, government bonds. So these are what I calculated as the asset classes of interest that correspond to the graph that I created. These are the risky assets. The average return is 11.4. The standard deviation 19.7% over that period. Government bonds as less risky at 5.2 and 7.8% standard deviation. But the risk-free asset, the T-bills, will be 3.5% with a standard deviation of 3.1%. What we want to do, looking at these asset classes together, is think about the risk premium. The risk premium is a measure of, on average, what is the premium required by investors in risky assets over and above T-bills, the risk-free asset. So rather than purchasing T-bills at 3.5% return, investors invested in the stock market risky assets will have on average an expected return of 11.4%, which is $7.9% higher than T-bills. We call that the risk premium. So this is that little extra that incentivizes investors with the means to actually purchase stock. I can also calculate the risk premium for government bonds. And it's 1.7%. So the risk premium for government bonds is not as high as that for common stock, because common stock are relatively more risky, as noted by the standard deviation, much more volatile. Okay, so I'm going to stop there. I'm going to leave you with this. I'm going to put some exercises into Connect. Also encourage you to calculate the risk premium for all the asset classes here, just so you can practice that and put it in your mind that that's something that we're going to look at. Okay. All right. If you don't have any questions, I'm going to stop there and talk on Wednesday. We'll pick up then. All right. So again, review the statistics videos, look at Connect, and I'll see you on Wednesday.